All right, let's get started. So today's plan is finish those discussion questions. And we also have two additional MCMC algorithms that we get to introduce. So I think let's do the discussion questions first, and then the other part of the small lecture. And then if we have more time, feel free to leave early for the break or work on lab 3, okay, whichever you prefer. So we have 4 remaining discussion questions from that paper, as you recall, and many of you made comments and responses already, so that's great. So let's start with 6, because I think that hopefully generates more activity as well as engagement, because this will be a little bit, I think, easier to discuss, and also involves a lot of the process of how to do a Gibbs in a particular case. So this is from the paper section 4. The authors claim a defining characteristic of the Gibbs sampler is that it always uses the full set of univariate conditionals to define the iteration. The question goes, explain this claim by illustrating how a Gibbs sample works with K parameters. I think in class we also talked about it, but I know many of you on Moodle made very detailed responses to how to do with K parameters. So maybe before we talk about it together in class, spend 2 to 3 minutes with the person sitting next to you, and just talk about it a little bit, how you will do it. Of course, you will have to assume that you know each of the univariate conditional distributions. So assuming that you know it, and then you can just talk through the process of coding up a Gibbs sampler by yourself in this particular case. Okay, so let's spend a few minutes on this. And for remote students, I think only 2, but I will do a breakout room for you too. All right, anyone wants to share just maybe in a very high level, what would you do when you have K parameters and you're trying to create a Gibbs sampler, assuming that all of the univariate conditional, full conditional posterior distributions are available? How would you do it with K parameters? We use theta as the generic notation for each parameter. And then, of course, if you're working with like the normal example, then we have 2 parameters. So you get theta 1 and theta 2. So one of them is mu, the other one is phi or sigma, whichever you use. And I think there is one example in our written exam. If you remember, there is a model with 3 parameters. Okay, so of course, it depends on how the model is set up. The number of parameters can change. So here we're talking about the generic case of having K of them. So if I'm trying to figure out, and I also remember in class we had that discussion of, well, if you have K parameters to code a Gibbs sampler, how many initial values you need, right? So that's another stuff that we discussed in class. So we can touch on that later as well. So if we just go with the order, like without loss of generality, theta 1 through theta k, so you will get your particular draw, I guess, that just use little s to represent it at the s iteration, okay? And you will generate that. So, well, we have the full conditional, so you will generate, so let me use, okay. Yeah, so you can actually generate this from the full conditional posterior distribution for theta 1, okay? Given, I think, let's just use y to represent the entire data set. And then, of course, your theta 2 from the previous iteration, theta 3 from your previous iteration, up to theta k from your previous iteration. Okay, so we write it this way. Of course, the full conditional posterior distribution is something that you derive, and then you figure out what it is. And then for us, we need to make sure that all of the theta, like all of the other thetas other than theta 1, they're coming from the previous iteration values. Okay, make sense? That will be the first step that you would do in the particular iteration S for theta 1. And then when you move on to theta 2, you will draw it from its own full conditional posterior distribution, and just make sure that here in the previous step, I already have a new draw for my theta 1. Okay, that's at the S step. But then everything else will still be from the previous step. And that will be the generic notation. And you do that until you get to the kth, which when you draw, I think is conditioning on all of the current draw in iteration S for all of the other parameters. Okay, overall makes sense, right? Yeah, and since if we're doing theta 1 as the first step, and you can see that well, whenever you're doing for theta 1, you need draws for all of the other thetas. So that's why in class we talked about previously that if I have k parameters, if I want to initialize the Gibbs sampler to go, and you have initial values for k minus 1 of the parameters to start with. Okay? So in class, I think we started with the simpler example of only 2 parameters. So you have theta 1 and theta 2 for that mu and phi example in the normal case. And when that happened, we discussed that, well, you need to know either the initial value for mu or an initial value for phi, and then you will get it wrong. You don't need both. Okay, so that's the reason. And then generically, when you have k different parameters, this is what you're gonna do. Okay, so you see that this is, well, because we're doing Gibbs, and then Gibbs is defined that the entire set of univariate full conditional distributions need to be available. So all of those needs to be derived and then recognized. Okay, and you might have questions of, oh, okay, what if I cannot recognize some of this? And that will be the second topic of today, is sometimes you won't be able to get the actual full conditional posterior distributions, even though you try very hard to derive it, it might not be available distribution itself. Then there's some other algorithms that can help you sample for this particular theta. Okay, so keep that in mind. We'll get to that point as well. So that's for 6. And I think 7 is very similar to what we discussed on Wednesday as well, because we talked about the 2 different approaches, right? The one that we talked about in class, as well as the one that talked about in the paper. So if you're trying to get m different draws, independent draws from Gibbs sampler, you can either do m parallel draws or independent chains and then get the last draw from each. Or you can run a super long chain and then do the thinning and then make sure that you have m draws in the end. Okay, so those are the 2 main approaches. And I think for the lab, you get to practice one of them, and hopefully you're making enough progress on that as well. So I think just in the interest of time, and not very many people present today anyway, so maybe we can skip 7. And what about 4? So 4 is from section 3 of the paper. It is talking about a specific bivariate example. Okay, so let's spend a couple of minutes so you can talk to your neighbors about what you think. We didn't get many responses on Moodle, so maybe many of you didn't get the chance to think it through carefully yet. So let's spend a few minutes on this and then look at it together. All right, so this exercise is from, so let me share this one. I think hopefully it's easier to read. Yeah, so this is, the question itself is from section 3, okay? So like I said, section 3 gives us a toy example of this 2x2 matrix, of how the x and y itself, and then they're both binary, right? So we have a discrete case working through it. So the paper already gave us, well, the joint probability density function as we know. And then they already also give us the margin of x, okay? And the exercise is asking us to write out the margin of y, which is of course summing up the other direction, okay, when you're looking at a 2x2 over here. And then they also ask you to verify the a y given x and a x given y, which are given to you. So the first part is verify that this is true. Hopefully, I think is roughly straightforward once you work out the matrix algebra a little bit more. And then the second part over here is to also verify, if you look at the form a little bit carefully, this is trying to say that, well, those transition matrix they're working with, if I do y given x first, and then I multiply that with x given y, I will get back to x given x. Okay, so this is again thinking about how that connects to what we do with the Gibbs sampler, because we're doing it iteratively, right? And then you go to y, and then from y you go to x, but then essentially you'll be able to get back to the marginal distribution, and that's what you're hoping to sample in the end. Okay, so any comments? I mean, I first of all, I would first of all, give a shout out to Louis to give us such a detailed explanation in the Moodle response. So maybe we can use this as a basis to give an overall view. So Louis, do you want to share a little bit about how you worked it through, and then any remaining questions you might have?
Can I start with my question actually?
Oh.
So the way I understood it is that because we're looking at it like in this example, at least, it is we're looking at x, right? A function of x.
Yeah.
So that's why it starts with x first and then goes to y. Because I tried to do like the multiplication, just looking at it like, oh, but like if you switch it, then the order changes.
Right.
Which I guess is one of my questions. Like, right, if you switch the matrix just in the function, would that give you like a different answer?
Yeah, good point. So I guess you're talking about the order of this too, right?
Yeah.
Right. So if you think about, so intuitively, I would say if I start to do, let's see, yeah. So if I switch this to order, I would imagine that I will get y instead. Yeah, if that makes sense.
Right.
Yeah, so like I know you did the hard work of trying to multiply. So again, it's 2x2 matrix everywhere for those a's. Okay, whether you're doing a x given y or y given x. So that's what Louis has set up for us at the very least. And then the order of it. So we focus on this discussion question, focus on x itself. Okay, but if you focus on y and you do the other direction, I think that will produce you the version for y as well, because you can look at when you have two variables in this case, x and y. If you look at the marginal of x, then well, there are certain ways that you can do those multiplications to get x. But if you do that for y, I think it's just a different order, if that makes sense.
Yeah, because I know I tried to like expand the matrix and then I tried to multiply it, but I was getting confused.
Oh, I see. Oh, I see. Yeah. So, well, I didn't do the hard work that you did, so I don't know. But I would imagine if you tried the other direction, then it will give you the other one. Okay. So for those of you who are interested in giving a try, I think again, what Louis posted on Moodle is really useful if you want to compare to if you do the matrix algebra by yourself to see if you get something similar. Okay. So thank you. And with that, so instead of using my laptop, iPad. So let's look at the last question over here. I think it's question 5. Okay. This is from section 4. What is the fixed point integral equation in the bivariate case? How does it help illustrate how sampling from conditionals produces a marginal distribution? The hint is to check 3 equations. One is in section 3, and there are 2 others in section 4. Okay. So before we look at it together, there are more responses on Moodle this time, so I can also pick up some of the nice latexing people did over there. But before we get there, maybe spend a couple of minutes with your neighbor and then also remote students in that breakout room, and then we're gonna come back together. All right, so this is looking at the fixed point integral equation, which is actually a term that the paper talks about. They actually use equation 4.1, says that this defines a fixed point integral equation for which you have fx, which is the marginal distribution, as the solution. So Abigail, if you don't mind sharing what you did in this typing up and also the explanation, I think, because you have a nice write up over here and I can bring it up.
I think looking at the paper, they
Yeah.
kind of walk you through what the point h of x was. And it was another integral, so I kind of looked at that and incorporated the integral for what hx was. So that it ends up being a double integral. And then because you're taking an integral of the conditional multiplied together and then multiplying that by a marginal, you end up with marginal relative to x instead of relative to c.
I see. So I guess you're talking about the double integral, and then in here you integrate out y, and then outside once you multiply with the marginal of x, which I think is the solution, right, itself, then if you integrate out t, then you will get back to the marginal of x. Okay. Great. Any comments or remaining questions about this one? Okay. All right. Good. So if that is the case, like I said, the only other thing that we need to do for this paper itself is to work on lab 3. So like I said, lab 3 is a replication of one of the simulation studies, and then particularly the first one over here. So make sure that you give enough effort. I think many of you made a lot of progress on Wednesday already, but nevertheless, if you have any questions about any of the process, especially using, because we introduced a couple of more packages, in this particular lab, so you can, make side-by-side histogram, for example, using certain library to do that. And of course, also, if you want to simulate directly from a beta binomial distribution, we use additional R package to allow you to do that, because the regular basic R doesn't include a beta binomial random draw. Okay, so keep that in mind. So that's that. So let me stop over here.